Yes, my name is Heiko Herden. I'm working at the VDMA, which is the German Engineering Association, and I coordinate a lot of companion specification working groups, but I also am the chairman of the OPC UA for Machinery working group. And in this presentation, I want to show you what is OPC UA for Machinery and how does it help you. So I want to start with a question. I started with the same question yesterday in Norway. I asked how many people do know about OPC UA for Machinery, and I saw like no hand. So let's see if the same applies for Finland. Who has ever heard of OPC UA for Machinery? Okay, this is good. So Norway was more people, but here's more knowledge about machinery. In this case, about machinery. I can't say it for all. But okay, so let's get started. Why do we need to do something? So we have a lot of different machines and components and systems that are connected to each other. I brought a simple example here where we have a robot arm taking out luggage out of a container, putting it on a conveyor belt. And in this simple example, we already see a lot of different involved components. So we have a robot, we have machine vision, we have a gripper at the end of the arm of the robot, we have weighing technology on the conveyor belt, and we have an electrical drive in the robot and on the conveyor belt. And all those things need to work together, and they can already work together, but it's cumbersome. You need to put a lot of time and work into those systems to work together. And they should also be connected to, for example, an MES system, ERP system, a cloud, something on top level. So we need vertical and horizontal networking, but we need to put in a lot of work so that it works in the end. And what we want to achieve is the same that we already know from our personal life. So for example, you have a cell phone which supports the Bluetooth standard. And you have a car which supports the Bluetooth standard, and then you can just connect it. That's called plug and work. And this is the target image for us in industrial context as well. So I want to buy a new machine. I want it to support certain standards, and then I can just connect it and have plug and work. So how do we get there? Now, as I said, we want plug and work. So our target image is we want interoperability. And we already have interoperability. From Industry 3.0, we have proprietary communication. So it all can work together already, but it's not really working that good. And now with OPC UA, we can put everything in one meshed communication network. So this is the first step to get a higher interoperability. And the machine building sector said, okay, OPC UA is perfect. It's open source. It has security built in by design. It has various protocols for PubSub or for client-server communication. We have the chance to do semantic machine descriptions, and it's scalable. So I can have it on an edge device or on a full embedded Windows computer, and it works on everything. So this is what we need, OPC UA, but to really have the highest levels of interoperability, we don't only need OPC UA, we also need information models. So let's take a look at this. What are those information models? These are the companion specifications that we heard about already. Alone in the machine building sector, we have 40 active groups at the moment. So let's take a look at these groups. So this is how the VDMA is clustered in different domains. And I colored the domains that have a companion specification released in red already in blue, and the ones still working on a companion specification, so a release is expected in maybe next year, in orange. And as you can see, we have a lot of different groups there. So it starts with additive manufacturing, which is like 3D printing. We have air pollution control, automated guided vehicles. We have a group for compressors. More in the back, we have also a group for pumps. We have a spec for cranes. The Weihenstephaner standards were translated into an OPC UA companion specification in the food processing and packaging machinery sector. We have a group for high pressure die casting, for the cutting of flat glass. There is a group for gripper, a group for joining technologies. We have intralogistic systems, laser systems, length measurement technology, which is like coordinate measurement machines. Of course, we have the companion specification for machine tools, for machine vision. There are a lot of specifications for the field of mining, also a lot of specifications in the field of plastics and rubber machinery, for example, for extrusion or injection molding machines. We have a group for electrical drives, and many more, as you can see. I don't want to read all of them, but just that you get an idea. So we have a lot of different machines and systems which are worked on in terms of companion specifications. And now with these companion specifications, we achieve the next level of interoperability, because now we have domain-specific information models. But as you can see here, we are still not on the highest level of interoperability, because what we recognized is that in these different domains, some information are still the same. So for example, a serial number, a manufacturer, operation hours, the state of a machine. This is all information that is not just needed for one domain, not only for, I don't know, an extrusion machine, for example, but for all of them. So how do we deal with this? We could reinvent the wheel for each of those groups. That would be one possibility, but not such a good one. And so we said, okay, let's start a group that addresses those use cases that really fit for everybody. And this group is called OPC UA for machinery. So OPC UA for machinery is also a companion specification, but it's not for one specific domain. It is for the whole mechanical engineering industry. And we define harmonized basic building blocks for the broad use. Each building block then stands for a specific use case. So for example, one building block might be for machine identification. And these building blocks can then be referenced from other companion specifications. So for example, if the pump says identification is interesting for us, or the pump specification group, then they just reference from OPC UA for machinery the identification building block. Or it's also possible to take it as standalone model. So for example, if there is no specification for your specific machine or production or whatever, then you can still use the machinery building blocks as standalone model in your own data modeling. And so you could say OPC UA for machinery forms the basis for interoperability. Let's take a look at the target image. So we have a lot of companion specifications, and you can see it at the top, and I just put some there. There are many more that's shown with the ... in the end. But for all the companion specifications, OPC UA for machinery is the basis. So if I take a look at a specific interface, for example, of a laser machine, then I will find OPC UA for machinery building blocks for the very generic topics. I will find the companion specification for machine tools for the little bit more specified topics, and for the topics that are purely for lasers, so yeah, very laser specific, I will find the laser specification. And so in the end, in the interface, I will have the combination of 3 specifications of machinery, machine tools, and laser. Or the same goes for a woodworking machine. I would also have in the interface the combination of OPC UA for machinery and OPC UA for woodworking. And so here again the message is OPC UA for machinery is the base companion specification for the whole field of mechanical engineering. So this is how it looks in the end. So we have OPC UA, we have the companion specifications of the domains, and we have OPC UA for machinery. And now the common question would be, okay, so you said you have building blocks with specific use cases. What are the use cases that are solved already? And so these are the published use cases. So we have machine identification, component identification, machinery state, result transfer, and process values. And we are working on more use cases, of course. Currently, we are working on 2 very big use cases, or 2 big building blocks. One is job management. Here we, of course, also align with ISA 95 job control. And we have the field of energy management. And here we work in the joint working group power consumption management together with VDMA, OPC Foundation, ODVA, and P&O. And yeah, these will be the next big topics, but we, of course, will do also smaller topics in the next years to come. And what I like to do now is to show you the published building blocks, how they look in OPC UA. So let's start with machine identification. And the question that I might have in mind is, I look at a lot of different machines in my production and I ask myself, okay, to what machine am I connected here? Which machine is this? Who built it? What's the serial number? Questions like this. And now with OPC UA for machinery, machine identification, I get this information in the same way. So how is it solved in terms of data modeling? So we defined a data model with a machine identification type. And this machine identification type consists of a lot of properties. And as you might see, most of the properties have a 2 double point at the start of the properties. This means that they are derived from OPC UA Part 100 devices. The properties on the big column on the left are properties that are set by the manufacturer of the machine. So if you order the machine, these will be already filled out. The properties on the right are properties that are set by the user of the machine. So he might have his own asset ID or his own name for the machine that he puts in there, or has his location where the machine is standing. And in the end, most of those properties are optional, but 3 properties are mandatory. And this is the product instance URI, the manufacturer property, and the serial number property. And this is important because with these 3 properties, I will have a unique identification. So this is how the machine identification works. Now let's take a look at the component identification. And as you can see, it's very similar. Also a lot of values inherited from Part 100 devices. Some differences. So for example, I don't need a location because the component is part of a machine. So it already knows the location from the machine. We have one additional parameter, the device revision, also from Part 100 devices. And we only have 2 mandatory parameters. We have the manufacturer and the serial number. And in this case, we don't need to have a unique identification. So this is machine identification and component identification. If I use those things, the machine identification type and component identification type, I also have the advantage that I will find those objects in the server more easily. So for example, I have an aggregating OPC UA server on top, and I have a lot of machines and components connected. Then I can browse through those connected machines. So I will be in the objects folder at the start, and in this objects folder, I will find the machines folder right underneath it. And in the machines folder, I have all the machines listed that have the machine identification type. On the other hand, within the machines, I will have a machine's component type, which lists all the components of a machine. And of course, a machine could also be part of another machine, so that you have something like a sub-machine, so to speak. And with this, this model here, I have a clear structure of all the different machines and components connected to my OPC UA server or client. So this is the use case of machine identification and component identification. Now let's take a look at the machinery state. So where do we come from? Again, I want to see the state of all my machines because, for example, I want to know how good the efficiency is in my production, or I want to do KPI figures. And at the moment, I get a lot of different terms. So here's an example where I see working, running, executing, production, dry run. There could be more like ready, idle, I don't know. There are a lot of terms. And what we did now is we defined a machinery item state, which basically has 1 out of 4 states. It is either not available, which means I cannot, or the unit is not available, it might be switched off or in energy saving mode. The unit might be out of service, which means it is not functional and therefore doesn't perform any activity. We have the state of not executing, which means the unit is functional, but still standing still, so not doing any activity. And of course, there's the executing state where we have a functional unit, which is working at the moment or performing an activity. And with these 4 states, if I jump back to this picture, I will get a clear information about whether the machines are doing what they are intended to do, or if they are standing still or having an error or something. So from a machine view, I now get the information in a good way, and I could also take a look at the components, so I have like a component view. So for example, I have a barrage filling line here, which is on red light, which would mean the machine is out of service, and I wonder, why is it out of service? And I might take a look at those components involved here. So I have a conveyor, an injection, and a gripper. And if I take a look at the state, I will see, okay, the conveyor and the injection are both on not executing, which means they are functional but not working. But the gripper is not functional because it is jammed, for example. And so I know, okay, so the gripper is the component that is forcing the whole machine to stand still at the moment. So this is just one use case how to use the machine state. Another use case would be to do KPI calculations. So for example, I know that my production or my machine should be busy 8 hours. So I have a planned busy time of 8 hours. That's something that's coming from the MES system typically. And with the OPC UA for Machinery machine state interface, I will know, okay, I was in out of service for 2 hours, I was in not executing for 1 hour, and I was in executing for 5 hours. And with all those times together, I will get the actual production time, which is 5 hours. And so the availability will be 62.5% because I can take those 2 times, and I know my first KPI figure, the machine availability. And this is just with only those simple values that you have seen. And for us in OPC UA for Machinery, it's very important to keep it simple because we want it to fit for everybody. And if we make a very complex model, then many domains will say, oh no, this doesn't fit for us. So we kept it simple, but you can extend it. So for example, this is the state machine that I have just explained with not available, out of service, not executing, executing. We said you can transition from every state and every state. We don't want to restrict anything here. And this can be extended by substates. And this was done already. So we have the extrusion companion specification, which took the state machine and defined substates for the state of executing. They said, for us, executing can either be a manual run or a controlled run, or it could be ready to run. And I think this is a perfect example because for most domains, ready to run would be a not executing because the machine is just standing still. But for extrusion, not, because the extrusion machine needs to heat up all the time to be really ready to run. So it has to do something to be ready to run. And that's the reason why in this case, ready to run is in executing in the substate. And there you see why we picked this modeling approach. So we have the simple basis in OPC UA for Machinery, but the domains can do substates so that it fits for their specific machine. So this is the machinery state. And with a glance on the clock, I think I need to speed up a little bit. We have 2 more use cases. Those are not so generic. They are a little bit more specified. We have result transfer. This is for complex measurement results, for example, from a machine vision system. Or if you have a coordinate measurement machine, you get a lot of data points. This is in one file, and you want to transfer the file. And so this is what this is done for. So we have like 4 or 5 groups that use this already. And it's about that you want to be notified when the results are ready, that you want to access the results, filter the results. And so we defined different mechanisms to get those results so that not every group has to think about an own solution, but we have one solution at hand that the groups can use if they have such a complex measurement result. And this is OPC UA for Machinery part 101, so it's a little bit more specified. And this is OPC UA for Machinery part 2, where we have process values. This is about that we show, for example, a temperature of a machine in the same way, because at the moment the format would be different in different groups, and yeah, we have a harmonized information model for that, so that now, for example, the temperature will be shown in the same way. You can still use different engineering units, of course, but it's in the same format. And we have a lot of requirements that we had a lot of requirements that we fulfill with this building block. So you can have an actual value, of course, which you get from a temperature sensor, for example. You could have a set point value. Of course, we want to have an engineering unit. We just saw it, Kelvin, Celsius, Fahrenheit, whatever. We might have instrument range on the sensor. So for example, if you take your oven in the kitchen, it usually has an instrument range of 250 degrees Celsius, and then it's good. We have deviation limits and general limits. We have a status whether the value is in range or out of range. We have alarms. We have a 0-point adjustment, which you usually have on a scale, for example, a kitchen scale, if you think about it. We have a substitution value if the connection gets lost, so that we have a set value in the system, and device information, identification and health. And many of those properties are derived from the PA-DIM companion specification, because what we always do with OPC for machinery is we take a look at what is existing already and what can we use, because we don't want to reinvent the wheel in OPC UA, where we want to use what is out there, so it works together in the end. So this was my presentation. One more summary here, so that you know, okay, OPC for machinery forms the basis for harmonization in the machinery and plant engineering industry. It is structured in building blocks, so you can use only some building blocks or all building blocks, whatever you need. Each building block stands for a use case, and many building blocks are already available, and it will be more in the future. And yeah, like I said, it can be referenced by other companion specification or used as standalone model. And of course, again, the important message that already Stefan mentioned, the standards are free of charge. You can just download them, take a look at it, use it. And so this is my message to you. Take a look at OPC for machinery, consider using it. And if you have any questions, feel free to contact me. I'm here all day. And thank you for your attention.